Hi guys, welcome back. So today we're going to be looking at partial fraction decomposition. And I went to go film a video on integration by nonlinear substitution first, and then I thought, hold on a minute, I'm not sure if these guys actually know what partial fraction decomp is. So I'll just write like the original problem. This is actually a worked example in your textbook. It's something like this. This is on page 334. So it's x minus 3 divided by x squared minus 6x plus 13 dx. And it's asking you to solve that. And you can go ahead and look in your worked examples and you can see what that question is and how to find it. But I think the easiest way to do that is by partial fraction decomp, right? So instead of having all these x squareds and all this crazy business, we're just going to deal with some simple numbers where x to the power of 1 is going to be the most difficult thing that we are dealing with, or x to the power of negative 1, I should say, is probably going to be the most difficult thing to deal with. And that's going to make this whole process of integration a lot simpler. So I know that this is probably a little bit off topic, but it is a really nice process. It is very algebraic. I do enjoy it. Okay, so the first thing that we are going to do is we are going to factorize the denominator. Okay, so for this first one, x is a common factor of x squared and x. So this is going to become negative 5x plus 4 over x minus 1. And so now what I can do, I can write this as a sum of some products. Okay, so what I mean by that, if I have this number here, right, or this factor here, right, I would have had to add that factor to some value for this factor here. Okay, and so this factor and this factor, they're going to add up to get this value here. Now, with this, what we can do, or what we should do when we're adding fractions, is we should have things that have the same denominator. So to do that, I'm going to multiply this by the other factor. So this is now going to become x minus 1 over x minus 1. And then I'm going to do the same thing to this. I'm going to make sure that that denominator is the same by multiplying it by x. So this is going to become bx over x minus 1. And so I hope that you can appreciate that if I write negative 5x plus 4, that that's going to be equal to x minus 1 plus bx. Okay, so now that we've got that written down, what we can do is we can expand this out and we can solve this. And we can do that by letting x equal to particular values. So, so step 1 was factorize denominator. Step 2 was to make like fractions. So when I say make like fractions, I mean make the denominator the same. The next thing that we are going to do is we are going to substitute in values for x. So substitute in values for x. So what I want to do is effectively, I want to only deal with one unknown at a time. So I'm going to get rid of either the a term so I can find out b, or I'm going to get rid of the b term to find out a. And to do that, I can make this factor in here equal 0, because if x minus 1 is 0, then this is going to cancel that a term and I'll be able to find b. Similarly, if I let this factor here equal 0, b times by 0 will be 0, and so I will only be able to work out what a is then. So for the first one, what I'm going to do is I'm going to let x equal to 1. So substituting that in, I'm going to get negative 5 lots of 1, which is just negative 5, plus 4. And that will be equal to a1 minus 1 plus b times by 1. So a times by 0, that's going to remove that particular term there. And so we can write b is going to be equal to negative 1. Pretty straightforward, pretty algebraic. All right, so now what we can do is we can do the same thing, except we're going to let x equal 0 this time. So that's going to get rid of that term and we can work out what a is. So negative 5 lots of 0 plus 4 will be equal to a times by 0 minus 1 plus b times by 0. So that term there is now going to cancel. And so negative a is going to be equal to 4. So a will be equal to negative 4. So we've got our two values for a and for b. So what I'm going to do now is I'm going to substitute those back into this original expression here. So I'm going to substitute in my value for a and my value for b. Okay, so this is going to now become, what was a, sorry? Negative 4 over x plus, what was b again? -1. Sorry, so that should be minus, but I'll just do this as plus minus 1 over x minus 1. And so now if we were going to integrate this is going to be a lot easier to integrate because we'll end up with -4 ln of x minus ln of x minus 1. And that's it. That's done. That's the integral finished. Ooh, plus c. Why do I always forget plus c? Okay, so this is getting a little messy. So I'm going to ignore the integral sections for the second, but I just wanted to show you why it was so important that we do the partial fraction decomposition. So let's do another example using that second question I've got up there. Okay, so step 1, we had to factorize the denominator. So let's do that. So we've got 3x plus 10, that's not going to change. Now this is a quadratic, so let's try using a factorization method. Are we going to have two factors of 20 that are going to add to 9? Yes, we do. That's going to be 4 and 5. So this is going to become x plus 4, x plus 5. So I can rewrite this fraction now as the sum of some number, which I don't know what it is, over x plus 4 plus b over x plus 5. Now, step 2, make the denominators the same. So to do that, I'm going to cross multiply. So I'm going to multiply the bottom and the top by x plus 5 here. And for b, I'm going to multiply it by x plus 4. So now we have 3x plus 10 over x plus 4, x plus 5 is going to be equal to this plus this. So if I was to just write out the top term, the numerators, we would have 3x plus 10 is equal to a x plus 5 plus b x plus 4. All right, step 3, we're going to substitute in values of x that are going to make these factors equal to 0 so that we can only deal with one term at a time. So for the first one, we're going to substitute in x is equal to -5. So we have 3 lots of -5 plus 10 will be equal to a times by -5 plus 5 plus b times by -5 plus 4. Okay, so 3 times -5 is going to be -15. -15 plus 10 is -5. This is going to cancel, and so I'm going to be left with this. So b times by -1 is going to be equal to -5, so therefore b will be equal to 5. Okay, let's do the same thing now, except we're going to use x is equal to -4. So then we're going to have 3 lots of -4 plus 10 is going to be equal to a times by -4 plus 5 plus b times by -4 plus 4, which is going to cancel, so I'm not even going to bother writing it. -12 plus 10 is -2, and that will be equal to a times by 1, so -2 is equal to a. All right, so I've got my value for b, I've got my value for a, so I'm going to substitute back into this original expression here, and that's going to give me -2 over x plus 4 minus, plus 5 over x plus 5. And again, I know I said I wouldn't do this, but I'm going to do it anyway. If I was trying to find the integral of this crazy function here with respect to x, instead of doing this crazy function, I can now do it on the partial fractions. It's going to be a lot easier. So if I was to integrate this, I would end up with -2 ln x plus 4. I always do that with the brackets. It has to be the straight brackets because logs can't deal with negative numbers. And I always mess that up. And, and of course, I've always got to add C on the end. I'm going to do that nice and big. My name is Cassandra. Why can I never remember to add the C on the end? It's bloody my name, my first letter of my first name. Alrighty, so that was partial fraction decomp. Have a go. I think I've uploaded a worksheet to your eLearn accounts. If you can't find that on the eLearn, it will be in the Term 2 folder. That's alright. Jump on to Google and just have a look at the Kuta Software one. So that's Kuta software and then partial fraction decomposition. And there's a fantastic worksheet, and that's where I've gotten these 2 questions from. And they also have the answers on there as well. Alrighty guys, I'm going to jump into the next video now. We're going to have a look at integration by nonlinear substitution.